afternoon to everyone. Thank you for attending this final webinar that we are organizing. Today, the webinar is focused on the environmental criticality and circularity assessment of materials and components for electrical vehicles. So we have four speakers from the project RHODaS, MTech, SCAPE, and Maxima. You can see the speakers here. Hello to everyone. Thank you very much for participating in this webinar. So we have 4 presentations. Each presentation will last about 15 minutes, and finally, at the end of the presentations, you can write your questions on the chat, and then I will ask the questions to our participants. So thank you also for attending this webinar, and we will start with Rainer Paminger from the Technical University of Vienna and from the RHODaS project. Hello, Rainer.
Hello. Hello. Sorry, wrong. So now it should be fine. Okay, hello again, and thanks, David, for your introduction, and thanks for the organizer from Mike, I guess, Nair, to organize this webinar. I welcome you to my speech. I will talk about circular powertrain solution, which I will talk about the work we did in the RHODaS project. I did this together with my colleague Philipp Feuchter. My name is Rainer Paminger. Short introduction to myself and where I'm coming from, working at the TU Vienna. We have there an Institute for Engineering, Design and Product Development, and a specific research area on eco-design. In this area, we're focusing, as the name said, eco-design is our core topic, sustainable product development. So this is based on the mechanical engineering faculty. And to do so, we focus also a lot on assessments, life cycle assessment, product carbon footprints, and the last couple of years also about circularity assessment in order to have meaningful results, in order to know the hotspots, in order to know where we have to go with our design. And additionally, eco-design is the last years we also focus a lot in circular economy meaning circular design on the one side, but also circular business models, as these go together. And we do a lot of method development, also a lot of tools I will show you later, trainings, knowledge transfer. Of course, we are at the university, and R&D projects with industry as also this project. It's clear why we're doing this. I just want to give 2-3 slides on this. We are actually using too much. You surely know the Earth Overshoot Day, the day on which all resources are already consumed by us, which would be available for the whole year for us. And we consume all our resources which are available already by the 24th of July. So meaning that if everyone would consume like us, we would need nearly 2 Earths. So this is too much, and we live be far beyond our means. Using too much means, also in terms of material consumption, too much means 14.5 tons per person per year. each of us is consuming 14 tons of materials. And some countries are less. We in Austria even consume more. So this is too much. So we have to do something about it. And what we can do is we can change our economy, and we could change to a circular economy, which is one way to go. And circular economy is defined as an economic system where the value of products, materials, and other resources in the economy is maintained as long as possible. And we should use those products, materials as efficient as possible in production and consumption, and thereby also reduce the environmental impacts. We should use it long and efficient, but we also use the environmental impact. And of course, we should minimize waste and the release of hazardous substances at all stages of the life cycle, meaning the raw materials, the manufacturing, the distribution, the use, and the end of life. So this was just a little bit of an introduction to my short talk here. Project RHODaS, we already heard about it. So the aim was, I would nearly say was or is, because we are nearly at the end of this project, to improve powertrains for heavy truck, electric transports, meaning e-trucks, using efficient new wide band gap materials like gallium nitride and silicium carbide in semiconductors. And we focus also on thermal management, but we also focus on circular design concepts. And the ambition is quite high, minus 20% in costs, minus 50% size reduction, weight reduction, and so on and so forth, and also 30% less in global warming potential. But to our talk on circularity, so what were our steps we went through? So we did a status check at the beginning on the 3 C's. We call it climate, circularity, and criticality, to know where we're standing, which information is available. Then we focused on the selection of the circular economy strategy. So we had here, have you developed a guided questionnaire? Then focused on circular design assessment. So we developed here design cards, and depending on the strategy, we have here specific design cards. Then we went into creativity workshops, idea generation, then selected the solutions, and additionally we focused on business models, where we used a different approach, where we used actually a kind of a strategy business model game. And I want to show you these 6 steps on our case study, electrical motor. So first step was this kind of status check, where we focused on these 3 C's. As I said, we did an LCA, cradle to gate, focusing on the motor, found out that magnets contribute 50% to the global warming potential of the motor, as you see here in the graph. So this all is coming from the magnets. Then circularity, we found out that actually the lifetime when the motor is coming back or is at end of life, or the vehicle is at end of life, the lifetime would actually be higher. Then magnets have also an economic impact. This is also important in terms of circularity. And other materials like all the metals can be recycled. Criticality also, magnets pop up here, including neodymium as critical materials. So with this knowledge, we then went into step 2, the strategy selection with a guided questionnaire. So we developed first, we defined the strategy. So, you know, these 9R, 10Rs, we wanted to simplify to nail it down to just 3Rs. Yes, so we have defined here short loop. So meaning if you are using it, your products need to be repaired or reused by someone else, this is short loop. Then if your product needs to be remanufactured, refurbished, then it's medium loop, or you go all the way back to the raw materials, then it's the long loop, it's recycling. So, and this is what we wanted to find out, which loop fits for the e-motor. And here we developed these questionnaires focusing on more or less these 5 areas where we ask question if is recycling technology available for the materials used, if components have high environmental impact, for example. So here it would be good to have an LCA before. And then, you know, in the end, which loop is relevant for your product. And for the motor, the medium loop was relevant here, so meaning focusing on remanufacturing was here the aim. Going to step 3 then was the circular design assessment with design cards. We have upfront developed design cards, about 70 design cards for the different loops, and for the medium loop, 34 design cards were relevant, and then together with the company or the employees, we're filling out those cards in terms of are they already fulfilled, are they not fulfilled, or are they not relevant. And for the motor, detachability of the connections was seen as relevant and not fulfilled. Low complexity of the disassembly, short disassembly, all these design aspects are relevant for further consideration. Yeah. So we then went into step 4, idea generation with creativity workshops. So we focused on the magnets, of course, because these are critical, these are relevant in terms of environmental impacts. We focused on the current e-motor, how actually we can disassemble the magnets. Here you can see the steps we have identified. So first we have to, so here you can see the motor, and here inside there are the magnets. And first we have to extract the shaft, then we had to cut the stack into slices, and then we have these slices, and they have to heat it up to get out in the end the magnets, and then we have to clean it to be able to reuse it. So this would be the way we could do it today with the current motors, but this is a lot of effort. So we looked also into new design concepts. So we have here different design concepts we developed in workshops with the product developers. I don't want to go into detail, but here you can see a lamination stack and a pole stack, and in the middle there is then the magnets, and this is all held together by a fiber sleeve with around it. Or here even we have powder, we just use powder. So this could then, if you think further, easily be reused. As you don't have magnets and the size doesn't change, so you can really use it again. But the difficulty is that the powder, if the motor is turning, is not allowed to move. Then we also have a cylindrical press fit defined, which is in terms of mechanics is kind of a standardized thing to do. What was the next thing? Step 4, we then evaluated those solutions in terms of how they perform in terms of technical feasibility, in terms of circular performance, in terms of climate performance, and also of course to focus on the economic feasibility. And so we found out that this first solution was actually the solution we want to go further. Yeah, we want to realize it. But in order to realize this, we also have to think about, in parallel, to think about the business models, because the motors are not coming back at the moment. So we have to think about how do we get them back to the component manufacturer. So in step 6, we then performed also within workshops. We used here a strategy game. It's called Make It Circular. It's quite a nice game and was really useful. So also the companies liked it a lot. And we came up with the idea with a leasing system for the e-motor. So, for example, if you have existing fleet, and you want to convert to electric motors, then it would be easy. But this is just easy in terms of, for example, for the London taxis vehicle manufacturers, as they are manufactured and operated together. So you have a contract as a component developer directly with them. But if it goes over OEM, it's a bit more complex. And because the OEM leases the vehicle to the end customer, and then the supplier has to have a kind of a leasing contract with the OEM. So this will get a little bit complex, but should be also somehow doable. This was the idea. Next thing was we also have to think about the supply chain. Supply chain, normally you have component manufacturers, then the OEMs, and then a logistic partner and the user, and that's more or less it. And then it goes end of life. But of course, we have to think about how to get it back. So we get it back via leasing model, and the vehicle user is giving it actually back by a logistic partner. So we have to think how we could do that. So we have additional partner here. Then this goes to a dismantling station where we actually have to evaluate the different components, if they go for refurbishment, if they go for recycling or whatever, or if they directly go back to the component manufacturer for reuse. So these all are now partners in an extended supply chain with those new business in terms of leasing model. So to summarize, for the e-motor, it's clear you have to go for remanufacturing. Reuse of the magnets should be focused on, and we focus on design for disassembly. And of course, new partners are needed, as you see it here in the supply chain. So it needs a kind of a really structural change, and really change the economic system how motors are sold. So this is what we also did then, not just for the motor, but also for the gearbox and for the inverter, of course. To finalize, I just want to show you two other projects we are doing at the moment. DC Megacharger in Austria, where develop and demonstrate 1 megawatt DC fast charging station, also for trucks, where we use also SiC technology. And our role is again here circularity, criticality, and LCA of the power stage. And another project I want to mention, which is also kind of interesting maybe for you, Circularity. It's an Interact project where we're already at the end now, where we supported companies in the electrical industry to implement circular economy in their products, in their business models. And we apply different tools. You can see here tools for LCA, tools for circularity, but also tools for business model and value mapping. As you see, we like tools. These are our tools which we have developed. You can they're free and online available. You can look at it from design tools, business model tools, evaluation tools. And with this, I want to stop here and say thank you for listening.
Thank you very much, Rainer, for your interesting presentation. Now it's time from Antonella Accardo from the Politecnico di Torino. Ciao, Antonella.
Hello, ciao. Thank you for
When
the
you want.
introduction, and I will share the screen. Can you see it?
Yes.
Okay, so first, a brief introduction of myself. I am Antonella Accardo. I'm professor assistant at the Department of Energy at Polytechnic of Turin and researcher at the Center for Automotive Research and Sustainable Mobility, CARS, in Turin. I'm pleased today to introduce you to this activity, which is the integrated LCA-LCC analysis that we'll develop within MTech for the assessment of electric motors and drives. And this activity is conducted in collaboration with Polytechnic of Turin, AVL, and Urban Gold, now MESOP. Here you can see the reference people within MTech that are working on life cycle sustainability assessment and the reference contact. Excuse me, I have some problem to slide. Okay, maybe some connection problem. So coming to the life cycle sustainability assessment that we conducted in MTech and the objectives behind. So electric mobility at state-of-the-art is often praised as inherently sustainable, but two key dimensions are often overlooked, which are life cycle costing and life cycle assessment. So our aim within MTech was to close this gap by integrating both methodologies to simulate and estimate in parallel environmental impacts and costs of electric motors and drives. The applications on which we focused on are two permanent magnet synchronous motors. One is an in-wheel motor and the other is an axial flux motor. So within MTech, we have objectives that are demanding not only in terms of performance, but also in terms of sustainability. In fact, for example, in terms of cost, we have to demonstrate that the cost of the motor is below €6 per kilowatt for in-wheel motor and €5 per kilowatt for the AFM. And in terms of circularity instead, we have to demonstrate that there is a reuse of rare earth resources that is higher than 60%. So our contribution to this analysis includes the development of a methodology framework and of a model that is parameterized and integrates LCA and LCC for electric drives, with the scope that includes the representation of both in-wheel motors and onboard motors, radial and axial flux machines, IGBT inverters, and both e-gear and mechanical gearbox. Reference applications are passenger cars, and the geographical scope of this analysis is Europe. This methodology framework and model has been validated on 4 case studies, 2 state-of-the-art drivetrains that we call it baselines, as well as 2 MTech solutions that we call it prototypes. And also the model includes the end-of-life submodel that is representative on one side for the baselines for representative state-of-the-art of motor end-of-life, and on the other side of potential optimum dismantling procedure to improve recycling and reuse of permanent magnets. So lastly, as I said, the end-of-life submodel includes the possibility to estimate the emissions and cost of recycling and also reuse. So the key benefits of this activity are basically 3. The first one is enabling holistic and robust evaluation of electric drive sustainability, enabling the quantification of benefits of recycling strategies and support circular economy and mobility. The team worked following this workflow that was basically introduced with the definition of the goal scope and then with the identification of two drivetrain solutions representative of the state of the art in Europe. So regarding this baseline is the identification, we identified as the state-of-the-art two radial flux permanent magnet synchronous motors that were designed or already commercialized in passenger cars and small vans. And for the E-VOLVE motor, we use it as the baseline, a drivetrain that is equipped with two electric motors developed by ELAFE in the past and an IGBT inverter, and this drivetrain is gearless. The reference vehicle in this case is the JAC IEV7. Instead, for the onboard motor, we use it as the baseline, the Volkswagen ID.3 chassis that is called the MEB platform. This drivetrain is equipped with an IGBT inverter, a permanent magnet onboard motor, and a mechanical gearbox. And in this case, the reference vehicle is the Volkswagen ID.3 Pro Performance. It is important to say that these two drivetrains, these two baselines are not meant to be directly compared, but they are the reference for comparison with the prototypes. Regarding data collection and system modeling and simulation, first, data have been basically collected from the partners involved in the project, and literature data have been used just to fill the gaps. The model has been developed within CIMAPRO, and the major LCA database was EcoInvent. So here I reported for the methodology. First, in general, that the functional unit for the results is one electric drivetrain comprised of one or more electric motors, inverter, gearbox, or e-gear, depending on the architecture. And instead, the system boundary is cradle to grave. So it includes all the life cycle phases from raw material acquisition to the end of life, and the components according to the architecture considered. On the left side, I reported the system boundary for the baselines, while on the right side, I reported the system boundary for the prototypes. Regarding the manufacturing, we basically use it, as I said, primary company-specific data for the manufacturing process, and it includes not only the energy consumption during the manufacturing process, but also the pre-consumer scrap that originates during the process and the emissions related to the transportation of raw materials from supplier to Europe. The model is built so that the default results consider virgin material only for the production, but it is possible to add optional scenarios where the effect of the reuse of some materials can be addressed, for example, permanent magnets, aluminium, copper, and steel. Regarding the use, this is the scheme of the methodology applied for the estimation of the use-based emissions. So as I say, the reference vehicles, so the JAC IEV7 and the Volkswagen ID.3 Pro Performance were used, and they were assumed to be guided, to be driven along a WLTC homologation cycle to estimate the energy consumption in kilowatt-hour per kilometer. Then this value has been integrated over a lifetime of 150,000 kilometers, and the so-called delta approach has been applied. So rather than allocating to the drivetrain the entire energy consumption of the vehicle, we decided to allocate to the drivetrain just the energy due to the drivetrain losses during the conversion of electrical energy to mechanical. Regarding the electricity mix, the default LCA model receives in input the average electricity mix, but also there is the option to substitute it with a more green electricity mix based on offshore wind turbines production in Netherlands, or a more fossil-based electricity mix based on hard coal power plants production in Czech Republic. So regarding instead the end of life, here we assume the different scenarios for the baselines and prototypes. So for the baselines, we assume that the drivetrain is dismantled from the vehicle, but then it is shredded without the dismantling of permanent magnets. So rare earth elements are not recovered, but only iron, copper, and aluminium are effectively recovered. Instead, for the prototypes, we implemented in the LCA and LCC the end-of-life procedure developed by Urban Gold within the project, that instead is a procedure in which the motor is not only dismantled from the vehicle, but also the permanent magnets are dismantled, and so that they are smelted and rare earth elements are recovered together with copper, iron, and aluminium. Coming to the results, I reported here just the results of the in-wheel motor prototype, and as you can see here, on the left side, we have the LCA results according to the indicators included in the EF 3.0 method. And on the right side, we have the LCC breakdown in the pie chart. For the LCA, we can see that in the carbon footprint results, the majority of the impact is due to the use phase of the vehicle. But in 10 out of 16 indicators, the motor production is an hotspot for the emissions. Regarding the recycling procedure that has been implemented in the model, here I reported a graph that is representative of those indicators where recycling is beneficial. So we can see, for example, in the first bar, that climate change is reduced by 59% with respect to the life cycle of the motor. Another perspective is the comparison between the MTech advancement introduced in the in-wheel motor prototype and the state of the art. So here I reported two graphs. One is representative of the carbon footprint, and the other is representative of the life cycle cost. And in both of them, the first bar is always the baseline, so the state of the art. So the MTech advancement demonstrated to reduce the carbon footprint in the scenario in which permanent magnets are recovered and the motor is recycled of 23% for the carbon footprint and 11% for the life cycle cost. We had also an additional scenario, which is the reuse scenario, in which we assumed that 60% of permanent magnets that are recovered are then reused in a circular way. So in this case, we have a reduction of the carbon footprint, which is 24% with respect to the state of the art, and 28% with respect to the 28% of the life cycle cost with respect to the state of the art. So coming to the conclusions, the climate change impact as well as the life cycle cost of the drivetrain strongly depend on the architecture, motor technology, vehicle type, electricity mix, and driving mission considered. But the recycling procedure implemented within MTech and implemented on the in-wheel motor as took as the example in this slide allows for a carbon footprint reduction of 29%. And if we compare the in-wheel motor proto against the state of the art, we can obtain a significant reduction with respect carbon footprint as well as life cycle cost, both in the scenario in which the motor is recycled and permanent magnets are recovered, and in the scenario in which there is a 60% reuse of permanent magnets. Lastly, this work wants to encourage novel design strategy for future electric motors and drives, since the design for dismantling procedure implemented in this model allowed us to significantly reduce the carbon footprint as well as the cost. So with this, I thank you for the attention, and I look forward to your question or any curiosity you may have.
Thank you very much, Antonella, for your presentation. About the questions, I want to remind the audience that you can write your questions, and finally, at the end of the presentations, we will have the Q&A session. So please write your questions in the chat, and later I will read them. So the next speaker is Mikel Fadul from the IREC. Hello, Mikel.
Hi, good afternoon.
Good afternoon. So when you want.
I will share the screen. I hope you can see it. Yeah. Well, good afternoon, everyone. Thanks for joining, and thanks for the consortium for organizing this webinar and inviting us. I'm happy to be here. I'm Mikel Fadul. I'm representing part of the team in SCAPE that have worked in the life cycle assessment of modular powertrains. And here we look at the first stage of the circular economy and the life cycle assessment. To give you some context about SCAPE, SCAPE is a European project that proposes a standardizable, modular, and scalable design of a power converter. And this technology, here what we are doing is designing a basic module of a switching cell that arranging several of these with some auxiliary components, we are able to build a working device that can already convert direct current to alternating current. This is important because in electric vehicles, we have to place one of these devices between the battery and the engine, because the battery works with DC and the engine works with AC. So in the end, to reach the power needed for the operating conditions of different electric vehicles, such as motorbikes, cars, or trucks, what we have is that we have to arrange several of these components for the different electric vehicles, depending on the type, we will have more or less. We will need more or less. Sorry. Then, to give you a sense on how this looks in reality, I wanted to show you a prototype that we built in the project, and you can see squared in red one of these basic models that I was talking to you about. I want to highlight that this presentation will refer to this prototype because it's ongoing work, so only for you to know. And in this project in SCAPE, we are not only were looking at the electronics and the electricity engineering of making this device reality, but also the objective is to look how this performs compared to ongoing commercial devices, and it's the goal, the final goal of this project. For this, we started looking at the environmental footprint of the prototype with a cradle-to-grave approach, and we used databases from EcoInvent and Spera for this, and the software used was LCA for Experts, previously known also as GARI. We estimated the emissions for the impact categories considered in the environmental footprint 3.1. And again, I want to highlight that this is ongoing research and results are not definitive. So going into details here, for the lifecycle inventory and the system boundaries, we considered, as I was mentioning before, the cradle-to-grave approach. with the manufacturing stage, and we separated the inverter part, so the electronics, from the aluminum housing. Then we also estimated the use emissions from the electricity losses, and finally, the end of life. I will go into more detail now, but I also want to highlight that the functional unit that we considered was the electricity effectively converted from the device. And we did this because in future stages, we wanted to be able to compare between different devices. And if we wanted to estimate the absolute emissions, we only had to multiply this number by the total electricity converted. So in the manufacturing stage, we considered all the energy and material requirements for the electronic components, and all of them have been considered, as well as other non-electronic parts. We also considered transport and assembling of these components, and with assembling was modeled mostly as the soldering of the electronic elements to the PCB. And then it's important also to mention that the electronic components were modeled from SPERA databases. And when possible, we retrieved information from material declaration from the different manufacturers to build ourselves these components. But when we say electronics, this is a bit vague and very general. So I wanted to highlight that we considered each transistor, resistor, and capacitor that is forming the device design here in this project. Then for the use stage, we consider the KPIs of the project, in a sense, 480,000 kilometers of use with an efficiency of 96.65 and a consumption rate of 15 kilowatt hour per 100 kilometers. Using this data together with the equation you see in screen that was retrieved from literature, we were able to estimate the electricity losses, and we used the electricity grid mix from the European Union to cope with to link for the emission. Then for the end of life, we considered transport, disassemble, recycling, and landfill stages. And in the recycling stage, we only considered the recycling of economically profitable metals with the specific recycling rates as expressed in literature. Then for the results, these are the results for all the impact categories. It's a bit overwhelming, I know, but it's pretty easy to understand. Each bar represents one impact category. For example, the second one is climate change. You have the legend in the bottom part of the slide. And what I want to share here is that recycling and housing that are depicted in orange tones in this graph represent a marginal part of the emissions and savings in virtually all the impact categories. Whereas electronics and electricity losses represent the majority of the emissions in all of them. Here I want to focus on climate change, and we will look at these major emitters. This is the same graph that I was showing you before, but only for CO2 emissions. We see here that if we expand the electronics, the emissions are concentrated in basically three components: the PCB, the thermal management, and the switching cell. Once again, if we expand and break down the switching cell, what we see is that transistors and integrated circuits form the majority of these emissions. This is because these components have silicon carbide elements, and they are highly energy intensive, which means that they require a lot of energy for their manufacturing. That then they are chosen because they have higher efficiencies than other devices, but we have the drawback of higher emissions in the manufacturing stage. Then looking at the emissions of the electricity losses, they represent the majority in 10 of the 16 impact categories assessed. But we thought that the assumption of using European average electricity mix was not the most accurate, because cars and vehicles in general will be mostly used and therefore charged in only one country. For this, we changed the electricity mix from European grid mix for 3 countries: Germany, Spain, and France, because they have different electricity mixes. We used data from 2020, which are from the data sets already in Ecoinment. And then using information from these own countries, we were able to model the electricity grid mixes that they project to have in years 2030. Here we have the results, again, only for CO2 emissions. On the left, the first bar is the European grid emission for 2020, which was the graph that I showed you before, the results I showed you before. Then the second cluster is the emission for Germany for the years 2030 and 2030. Then Spain for the years 20 and 30, and France for the years 20 and 30. We only buried the use emissions here. That's why the embedded emissions from the electronics, the housing, and the recycling doesn't change. And in the end, what we see here is that the emission from the use stage, there is a clear trend for them to reduce with time. This is because in the end, the energy transition and the higher penetration of renewables in the electricity system. What this makes is that regardless of the efficiency improvements, these emissions will decrease, which in turn shifts the responsibility of the emission from the electricity generation to the design stage itself. And we see that, for example, in countries like France, the embedded emissions are already higher than those from the use stage. Here we reach the conclusions, and firstly, in this study, we were able to pinpoint where are the hotspots of the emissions in this device, mainly in electricity losses, but then inside the device itself and what is in our hands to change, we find the hotspots in the thermal management, the PCB, and the switching cell, so the electronics here, the transistors and the integrated circuits more specifically. Then we think that we should focus on the embedded emissions from the conclusions of the sensibility analysis and look to extend the lifetime of the device through strategy of reparability and modularity. And for us, we look for future research to go further in our analysis for the final device and to compare it with a commercial one to see how this performs. And with this, I thank you for your attention. And if you have any doubt or any question, I'll be happy to answer them.
Thank you very much, Miguel, for your presentation. And now we have the final presentation from Lea D'Amore from the Maxima project. Hello, Lea.
Hello, thank you. I think to share my screen, Miguel, you need to.
Sorry, is it
No,
okay
it's
now?
fine. Yeah, it's okay, perfect, thank you. Okay, can you see it full screen? Okay, great.
Yes.
So indeed, I'm going to present a bit how we used life cycle assessments in the Maxima project. I'm going to go just through these slides because I think it was already well presented in the presentation before, and focus mostly on LCA for Maxima and our goal and scope first. So we looked into the new machine, the new electric motors that the partners in Maxima are designing, from raw material extraction to end-of-life management. And we included also an approach on recycling of PM, as one of our partners is expert on that. And the electrical motors, environmental performance, are also compared to a reference benchmark electrical machine. So regarding the indicators that we are looking into in the project, we are looking into climate change, but also mineral resources. And I'm gonna just dig a bit more on that topic here. So you have here the list of the different critical and strategic materials that are considered as such by the European Union, and highlighted are the ones that are needed to construct our electrical machine. And so mineral resources here was decided to be assessed to assess how we use this resource and their criticality. But for the methodological point of how to assess mineral resources, there are actually very different methods. I'm just going to explain a bit how they consist to. So a first approach is to look at the resource and their extraction. And there you can have some indicators that look at the extraction of exergy based on the use of your resource, but also just on the quantity of resources that you take out from the earth crust. The depletion of natural stock is actually an indicator that is the one advised by the European Commission from the environmental footprint framework. Other indicators can look into future consequences here of using a resources by looking at how it declined the ore grade and the additional energy and costs that you can yield from that. But there are also approaches that are looking rather into the reserves and the stocks of raw materials that you have. Here you have indicators that are looking at the vulnerability of the supply chain and are based on geopolitical or market-based factors. And you have one that is from the perspective here of the end of life, and look into the time a resource takes to get dissipated. And dissipated means that it's not recoverable anymore. So in Maxima, we are actually for mineral resources looking into these two methodologies. So the one that is advised from the environmental footprint, so on depletion. But what we noticed when we looked into the literature review is that some rare earth elements that are in our machine are not characterized in this method. And so this is one of the reasons why we went also with another perspective. And here we decided to choose the dissipation method that is looked more at characterizing resource based on end of life. There are no wrong choice of choosing one method over the other. It just really frames what you will be assessing then for your product. So now regarding the results for the project. So the LCA part in Maxima has been already implemented from the very beginning of the project. And this is a bit the kind of steps that we follow and are still following for as we are 2.5 years into the project. So first we started to look at the literature review of LCA of electric motors, and then also the LCA of the reference e-machine, where we could yield some first results and look into some hotspots. So for climate change impacts, what we noted from the review is that usually the use phase impacts are dominant, which means that the efficiency of the machine will be very important. From the production part, we saw that the main contributors were electrical steel and aluminium, if you only look at the production there. And of course, with recycling, you can show some benefits to lower the production impacts. Regarding depletion, here the dominant contributor is this time the motor production and actually the copper, which is largely dominant with this methodology. So the partners in Maxima developed different designs of electrical machine, different architecture, and we had to decide which one to choose. And there were different criteria that were based technical criteria, but also cost and also LCOs involved. And here, this is the type of results that we showed. So on the 3 indicators compared to the reference vehicle, here from a cradle to use perspective, how are the performances of the different machines. So in the latest versions, the first thing we noticed is that actually they were becoming better for all 3 indicators than the reference vehicle, mostly due to a reduction in the copper amount of the different designs. Another thing is that we don't have really the best machine because from climate change perspective, one version was better than the other, but then from the dissipation and depletion point, another machine was slightly better. So here it means also that you need to have within LCA also some kind of compromise. Just a focus on climate change because we noticed that the use phase was the main contributors. Here, we wanted to look also at different mix, the one from Poland that is fossil fuel based and the one from the Swedish mix that is decarbonized. The idea behind that was also that the machine will be used in likely to be on the market in a couple of years and then used even for decades later, and the electricity mix is expected to decrease. And here we see that then the motor production, even for climate change, become quite significant. Now, we added recently the different end-of-life scenario to this electrical machine. So how it is modeled, so we have our materials, our metals, the permanent magnet, and the rest, which is called here the light fluff. And what we assumed is that the light fluff would go into energy recovery. For the metals, a part would go to recycling and another to be disposed. And for the PM, depending on the scenario, it's either get lost within the metals or it could go into our partners' recycling process and become then secondary materials. Regarding end-of-life scenario, so we keep the same type of assumption for the rest of the material, except for the PM, where we look into a difference in recycling rate between 100% and 0%. So no recycling at all of the PM. So when we look first into climate change and depletion, due to the fact that the PM is not necessarily the main contributors, you see a slight reduction, but not necessarily a significant one. For climate change, more precisely, we expect also, if you look into a more decarbonized mix, that this reduction would be slightly higher. For mineral resource depletion, again, it's really the copper that is largely dominant here, and this is where the effort needs to be done with a higher recycling rates. Where we see a reduction is a 15% reduction here is on dissipation, where the PM really have a high burden at the level of the electrical machine. Here, what we don't see yet, and we will try to do as future research, is that with the process we have now, the permanent magnet is able to be recycled several times, so there could be a recycling loop here that is not assessed, but that we expect also will make the reduction higher. A final point is that during the project, we developed also an LCA tool that could be used by the partners. It's a tool that allows the partners to enter some mass of materials that they want. They can also model a bit the use phase, choose a mix and different type of parameters like that. Then they would click on calculation and they would see their results for the 3 indicators, combining also the 3 and for different design that they want to build. And we recently also added this notion of PM recycling rate and end of life on this tool. So to conclude here for Maxima, so the LCA was involved here in the criteria of the chosen design for the new electrical machine. It allows also to provide some insights on how the impacts may evolve over time. And it thrives and needs strong collaboration with the different partners. From the results, we had the chosen design that outperforms the reference vehicle for our indicators. However, so here, as we saw, the production phase remains crucial for a low carbon electricity mix. And here we see that the recycling of PM is very much significant for mineral resource dissipation. On a broader perspective, and still to see is this notion of prospective LCA and how it will look like to produce an e-motor in the future that is included in the project. And now we are trying to refine the data as the partners have and can provide us with the refining data. We need to look into this approach of recycling loop and look at the final LCA of the prototype that is not there yet available. And I thank you for the attention.
Thank you very much, Lea, for your presentation. So now it's time for the Q&A session. So we have some questions for our speakers. If you have any questions, just to remind you, you can write them on the chat and then I will receive the questions and I will ask them. So the first question is for Rainer. The question is the following. Do these circular design concepts also result in a reduction of the environment? Do these circular design concepts also result in a reduction of the environmental impacts, or are they just circular?
Yeah, thank you. Thank you for this question. Yes, we hope so. Yeah. We have a target in the project, which is 30% reduction in the global warming potential. And now we are kind of in the final stage of the project. And now it's time for the cradle to grave approach and to really calculate the LCA on a systemic perspective. So the calculating like the others did already, the other presenters in their projects, to really also include the use stage and the end of life stage, and to see really what this circular economy scenarios actually will bring in the end. Yeah, our problem is really that we have developed in our project a full demonstrator, and which is actually now at the test bench, and that we get this data soon, hopefully, and then we can also see if we really can fulfill this result. But as we really focused on the hotspots in terms of LCA, but also in terms of circularity potential, I think we are sure that we will get there. Also, I'm more confident because I saw the results also of the other presenters here, which focus on the magnets in this case. Yeah.
Thank you very much, Rainer. We have more questions. This one is for Antonella. The question is the following. How did you manage the primary manufacturing data provided by partners, especially considering that the motors were prototypes?
Thank you for the question. And of course, when prototypes are involved in LCA assessment, they should be treated properly. For example, adopting ex-ante LCA methodologies. But in this case, first for the life cycle cost, all cost entries are considered at industrial level, so assuming that the production already occurred in series. Instead, for the LCA, we have different cases for different motors. For example, for the axial flux motor, we, together with the motor manufacturer, developed two scenarios, one for the prototype production and one for the series production. So we have different data for different scenarios. And for the in-wheel motor instead, we only had data that were at prototype level. And first we look at the results and we saw that actually the relative contribution of the manufacturing emission is not so high. So we decided to not follow the path of an ex-ante LCA. But of course, the results of the manufacturing can be reduced significantly if series production of the in-wheel motor is considered.
Thank you very much, Antonella. We have more questions. This one is from Michael. Is the following question. In the sensibility analysis emissions, okay, the question is the following. If the sensibility analysis emissions go down because of the increase of renewables, but manufacturing emissions remain the same, shouldn't they also go down?
Yeah, thank you for the question. I imagine this is because of the change of electricity production sources. The thing is that we were able to know who were manufacturing the different components and more or less locate their factories. We assumed some of these. In some cases, we assumed this was in China, but most of the manufacturing, most of the components were manufactured in China. And the thing is that in China, I think they plan to peak their emissions by 2030 and then go down. So in this specific scenario, where we were looking at the 2030 emissions, if we had considered a change in the electricity sources, it would actually have increased. I mean, we could do it with a prospective analysis, but that would require a bit more time, and we were looking at a prototype. But that's the answer.
Thank you very much, Michael, for your explanation. We have more questions. We have two questions for Lea. Are the following. The first question is, what key elements are essential for LCA to meaningfully guide eco-design?
So here I think, so in the Maxima project, the main advantages is that the LCA was really part of the project from the very beginning. We had some project before where the LCA happened at the end, and so really you just do the LCA of the new products, hoping that it will go into the right path. But here from the very beginning, although you have some preliminary results and not necessarily the latest data, you can already identify the hotspot and tell that to the industrial partners that are designing the different machine. We really need to be involved as a transversal activity here with all the different partners and have good communication with them to always get updated for this data. So yeah, here being there from the beginning, also communication is important, although sometimes, of course, LCA comes at the expense of, it's more like the performance of the machine is a priority. So of course, it can come a bit at the expense of the LCA choice. We had a long discussion, for example, for the use of glue or not for permanent magnet, etc., this type of things. But yeah, these two elements, I think, are key here.
Thank you very much. And we have another question for you. It's the following. Do you distinguish between the materials that are used in the product, or do you only calculate the material used along the supply chain?
Sorry, can you repeat? What?
Do you distinguish between the materials that are used in the product, or do you only calculate the material used along the supply chain?
I'm not sure I understand completely, but we are considering for all materials that we have in our machine, we are calculating them from raw materials extractions to the end of life when we added recently the end of life. So that's how we model it. For the first results that I show, I stopped at the use phase. But here the use phase is considered within a car and it's related to the electricity consumption.
Maybe I can add here something, because I think I know where's the question coming from. Because we had a problem regarding critical materials, yeah, and we didn't get the details, yeah, of all the materials, all the critical materials in the product. Yeah, especially if you have supplier parts, then it gets really difficult. So you don't know the critical materials in the product, in the final product. And then, as you said, you are working with the abiotic depletion potential. You then have the full supply chain, everything included. So also the critical materials which are not in the product, but which are somewhere coming, in the production or something. Yeah.
Yes.
And this was the question: if you also have just the critical materials of the final product, if this is and how did you get them?
So basically, more specifically, for the permanent magnet, we had a partner actually that were able to give us the bill of materials for the different. So we knew exactly how much would get of these materials into the final products. Then if you go to the mining impacts along the supply chain, there you need the commercial database that we are using to get the impacts from that.
But if you think about other components like ICs or like other electronic components, you don't know the details in terms of critical materials.
No, there you need to use a proxy, and depending on the database that you have, or if you have access in our university, we have a part that is disassembling some kind of electronic part. So there we can get a type of bill of material here. Otherwise, you need a proxy of the final product indeed. And actually, in commercial database for ICT more specifically, it's not always the best estimation sometimes.
Okay, thank you.
Thank you for your answer, Lea. Thank you for your apportation also, Rainer. That's true. We had this problem on the RHODaS project that there are some, especially electronic components that we don't know what exactly what materials are inside these components, and this was a headache for all involved in the project.
I can send it to you later, but there is also from another university in Belgium an open database now for ICT. Maybe it can be useful also, where they also disassemble screens, etc., and they made it open access.
Yeah, thank you.
Nice.
Yeah, that's good. Yeah, because our problem is really if we use the LCA data, then you have the whole supply chain, and then it doesn't matter if you have a kind of electronic, a small electronic or a big one or this one. They are always the same. Or even we looked at I don't know, what was it? I don't know, a cucumber or something like this. Even you have a copper problem, yeah? And there's always the same raw materials in the supply chain somehow. I don't know where from they're coming, but you always have this problem. And this is, yeah, I think not so useful if you want to improve it.
Okay, so
I have maybe another question for Mikel, if this is possible, or you have another.
Of course. No. For the moment, we do have more questions, so feel free to ask Mikel.
Yeah. Okay. My question is: you said that you also using SiC-based ICs. Integrated
silicon
circuit
carbide.
also?
Yes.
Yes. And the question is, which data sets did you use there? Are there specific data sets in Sphera or?
There are specific data sets, but not for silicon carbide. What we did here is that we use some literature that looks at the energy requirements for silicon carbide transistors, and depending on the footprint of the device, we were able to guess which amount of energy and electricity was required for their manufacturing.
Okay. Thank you. Yeah. Similar.
But also to what you were mentioning before, there are some, I don't know if it's helpful, but some manufacturers post I don't know how reliable this is, of course, but they make public the material declaration of some component.
Okay. Which ones, or?
Well, depending. There are some. If you look, I mean, we were able to pinpoint the specific model because we are designing the product ourselves. But I mean, I can show you later, or we can have a chat. But if you Google the specific name of the component and you go to the website of one of these vendors, don't remember the name exactly, but it will pop up in Google, the first or second link. You can look for material declaration, and then there is a file with all the materials and the percentages and the weight that compose these elements. You don't have the energy required for its manufacturing, but at least you have the material.
Okay, thank you very much. And I have one question for Antonella as well. As you said, you also included the dismantling of the magnets.
Exactly.
Did you test this, or did you how did you calculate the efforts for doing this? Because I don't know if you have seen my slides, but I showed the steps how to do it. Maybe you have a different design of motor, I don't know, but I guess that the steps are similar. Do you have here data which you maybe can share with us?
Thank you for this question. And I saw your slides where you are at all the details. In this case, I was not the project partner directly involved in the procedure for the dismantling, because this is in charge of Urban Goals. As you can see, and as you have seen in my slides, we have 3 of us working on that, and Urban Gold is the partner that was involved in the development of the dismantling procedure and recycling of permanent magnets. As far as I know from my side, the Urban Gold, together with the motor manufacturer, agreed in these years on where design strategy, what kind of design strategy to apply for the permanent magnets. But I suggest you to contact them directly. And Urban Gold was in my slide. One of them was one of the reference contact in my slides, so can be more precise than me.
Yes. Okay. I will contact you first, and then we can.
Okay. No worries.
Have a chat. Okay. Thank you.
Okay, for the moment we don't have more questions, but someone put in the chat that for some components they think that the material declaration is compulsory in Europe. Talking about the topic that we were talking earlier. I don't know personally. I don't know if for some components it's mandatory. The experts are you. I really know that it's true that the manufacturers from some machinery and companies have to declare that have to comply with the RHODaS directive and the WEEE directive and so on. I don't know if you want to say something about this this statement. No? Okay. Okay.
Well, I know in automotive there are those material data sheets. I think they are kind of standard, but they are very detailed somehow, and I think on elemental level, if one gets that, I think there are also the critical raw materials then also declared. But in RHODAS, I think it's more focusing on the hazardous materials.
Yes.
So there, it's not all the whole bill of material. It's just But of course, this is very automotive focused. I don't guess in other sectors, material data sheets are not common. Yeah.
Okay, so we don't have more questions. So thank you everyone for participating in this webinar. Thank you, Rainer. Thank you, Michael, Leah, Antonella. Thank you very much for being here, for collaborating in this webinar series. And thank you also to all viewers that have been with us during this full webinar series. So that's all. So I hope that you will learn something new in these webinars, and see you on the next webinars, or maybe in the final event of the RHODAS project. So thank you very much, and have a nice day.
Thank you, David.
Thank you for organizing.
Thank you, all of you. Bye-bye.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.